All right, AP Stats, how we doing today? Happy Friday. Today, go ahead and get out your notes packet. We are going to talk about doing confidence intervals. Today we're going to talk about it for a mean problem. When we're talking about a sample mean. So give you just a second to get out your notes and get ready, and then we'll jump into this and get going with this. So I'll give you about 5 seconds. All right. Hopefully you all have your notes out and ready to go. If not, hit pause real quick and then make sure everybody's ready to go, but we're going to continue on. All right. So for estimated population mean, there is quite a bit more stuff that can happen when we're estimating a population mean than can happen when we're estimating a population proportion. So there's a lot more going on with today than there was from Wednesday. The basic setup is still the same. We're going to take our statistic and we're going to add or subtract our critical value times the standard deviation from the sample. So our basic setup is the same. Our sample mean plus or minus our critical value times our standard deviation from our sample. The first thing that happens, though, is this T star versus a Z star distribution. So I'm not going to spend a lot of time talking about a T star distribution because it's not something that's heavily hit on AP, but I do want to spend a little bit of time talking about it because it is something that AP will hit. So those of you taking the AP test, you'll need to have a little bit of an understanding of T star. Everybody will have to understand how to find it and how we work with it. And so the basic idea behind a T star distribution comes from this sample standard deviation. And there's a lot of things here where a lot of students will go, why? But I thought, and those are all valid questions and things like that. But the essential idea behind why we have to use a T star distribution is when we find a sample standard deviation from a sampling distribution, the formula for this is the sample standard deviation is the population standard deviation divided by the square root of n. Okay, but we don't know the population standard deviation. And because we don't know the population standard deviation, we have to give ourselves more wiggle room, more room for error. And so what we end up using here, instead of the population standard deviation, we end up using the sample standard deviation S sub x, the sample standard deviation. So the standard deviation formula for the sampling distribution of x bar is actually equal to the sample standard deviation over the square root of n. Now, because we use the sample standard deviation instead of the population standard deviation here, just like when we were talking about that clear back in chapter 2, dividing by n versus dividing by n minus 1, we used n minus 1 with sample standard deviation to give ourselves more room for error. The same thing happens here. Instead of using a Z distribution, we use a T distribution. Oops, that's supposed to be a T. Now, here's the thing about a T distribution. You see that I've intentionally drawn it differently. I have given myself more error on the tails and less area in the middle. What that does is if I want a 95% confidence interval from the Z distribution, this is a little bit high over here, in order to get that same corresponding 95% on a T distribution, I'm going to have to go out farther. So 95% on the pink distribution has a little bit farther out than it does on the blue distribution, on the Z distribution. That gives me that much more room for an error in my calculations or in my sample mean and my sample standard deviation. It gives me that much more wiggle room to make sure that my confidence interval is accurate and catches the true mean. It makes it that much wider, giving me that much more opportunity to catch it if it was really a really extreme population mean that we were actually trying to find. Now, every single t-distribution is slightly different. There are different t-distributions, and that's really weird too. Here's the way it works. As we get a bigger and bigger sample, what do you think happens with that t-distribution? As we get more and more sample data, our distribution should become more and more accurate, shouldn't it? So as my sample gets bigger, my results get more accurate, and so my distribution gets closer and closer and closer and closer and closer and closer to that z distribution. So this particular t-distribution that I drew right here might come from a sample of size 3, where I only gathered 3 pieces of data. Well, if I only gathered 3 pieces of data, my estimate's going to be a long ways off, so I have to give myself a lot of wiggle room. Contrast that. If I were instead to ask a sample of, say, magic number 30, I still won't be quite as exact as the population, but I'm going to be way closer to that population. It's really hard to draw this very accurately with these pens. But my sample of 30, it says n equals 30. That green pen doesn't show up very well on this screen, so I'm sorry. But that sample of 30 should be way closer to my population distribution than a sample of 2 would be. So out here on the tails, that 30 distribution, that green distribution, is a whole lot closer to the blue distribution than it is the pink distribution. Okay, so whenever we talk about t, notice you'll say right here, whenever we talk about a t distribution, we must always include the degrees of freedom, and remember that's n minus 1. Just like when we were dealing with the sample standard deviation from chapter 1, we dealt with n minus 1 in the denominator instead of n. I don't know if you remember that, back to standard deviation of the population versus standard deviation of the sample. This was divided by n, this was divided by n minus 1. We were finding that standard deviation. And so just like when that sample standard deviation was divided by n minus 1, my t-distribution has n minus 1 degrees of freedom when we talk about a t-distribution. So there's a lot there, and I'm not going to go into it a whole lot more now. We'll talk about it more on Tuesday if need be, and we can clarify that a little bit more on Tuesday. But it's basically like this. If this is my z distribution, my t-distribution is always going to be less area in the middle and more area under the tails out here. And so we're going to be using t-distribution when we're looking for the area under the curve. We give ourselves a little bit more area, a little bit more wiggle room. Now, the nice thing is when we go to our calculator to do inverse t, you'll know that you're doing the right thing or not based off of what the actual screen prompt says. So inverse t is in that same place that inverse norm is at, in that distribution menu. So second, distribution, and you'll notice right down below inverse t is tPDF, tCDF, and as we scroll, sorry, it's literally right below inverse norm is inverse t. I looked at the wrong place. So right below inverse norm is inverse t. We also have a tPDF and tCDF. We will not do that. That would be to find the area under those curves. That's not something we're going to have to do. We will only be using inverse t. So in your calculator, you're going to go to second bars, which is your distribution menu. Scroll down to inverse t and press enter. And you'll notice that it says, what is the area we're looking for? Notice that now, even with my new version of the calculator, I do not have that opportunity to say left, middle, or right. So I have to use the 1 plus c divided by 2 here. So if I'm looking for a 95% confidence interval, I'm going to do 1.95 divided by 2. And let's say that my sample had 30 people that I was measuring, so my degrees of freedom is 29, n minus 1. Now, you'll notice that when we get ready to go do this calculation, if it was a z distribution with a 95% confidence interval, it was 1.96, or really close to 2. Now with a t distribution, that number is actually going to be slightly above 2 instead of slightly below 2. Just like we talked about, it's giving ourselves just a little bit more wiggle room. It's pushing that margin of error out a little bit farther on that curve to give us that little bit of extra wiggle room. If I do that same operation, and instead of a sample size of 30, I use a sample size of 300, so my degrees of freedom would be 299, that's a huge sample. This is going to be much more accurate. So it's a whole lot closer to the 1.96 that I got from an inverse z. If I did inverse z, or inverse norm, notice I get 1.9599. What do you notice about these results? So this is the z distribution, the 1.959996. This is the t distribution with a sample size of 300. This is the t distribution with a sample size of 30. Notice, this is the smallest distance away, and this is the largest distance away. My sample size was 30 here. I had to give myself a whole lot more wiggle room. My sample size was 300. That's a pretty accurate sample. I needed less wiggle room, and here would be theoretically the entire population if I knew it. So that would be my exact 1.95996 standard deviations. Hopefully this is kind of making sense as to why we use t and also what that actually does. It gives us more wiggle room, a wider margin of error to account for our variability that we know is going to happen. All right, continuing on. Let's practice this. So as we talked about last class, letter A down here, we know that this is going to be a t-star distribution because it's talking about a means problem. So to find that t-star critical value, and I always do this. I always leave it up when I'm doing t versus z. I notice I draw it and connect it all the way down. On a t, I intentionally leave it up. That's a reminder to myself that I'm using t. I'm giving myself more error under the tails. So I'm looking for 96%. So this area is 0.96. I'm looking for this t-star critical value. So I'm going to do inverse t. My area is going to be 1.96 over 2. And remember, with inverse t, we always have to give the degrees of freedom. So in this case, if my sample was 22, I'm going to use 21 degrees of freedom, n minus 1. So on my calculator, distribution, inverse t, let me get where you can see that, sorry. Inverse t, 1.96 divided by 2, and 21 degrees of freedom gives me a t-star critical value of 2.19. And again, I want to contrast something for you here. Notice t-star 96, z-star 96. A little bit bigger t-star value than we had with a z-star value. With the mean, because we know that it's more estimated, we're giving ourselves more room for error. That margin of error is going to push out that much farther on the distribution. 2.054 is going to be here. 2.19 is going to be here. We've pushed that distribution, that margin of error, just a little bit farther out this direction on that curve to give ourselves a little bit more room for error. Okay, real quick. Try letter D on your own. We know that this is going to be T star because it's means. So I want you to practice finding T star on your own. And by the way, if you're just sitting there waiting for me to put the answer down, you're not going to understand this very well. You need to go do it yourself. So, inverse T on the calculator, should be an equals there. Inverse T, my area is 1.99 over 2. My degrees of freedom is 70, because again we do n minus 1. So on the calculator, inverse T, 1.99 over 2. My degrees of freedom is 70. Sorry, you can't see that. There we go. Inverse T, 1.99 over 2. Degrees of freedom of 70. And I get a Z star critical, or T star critical value of 2.648. Okay. Hopefully you guys got all that copied down. Now, how do we use this? How do we actually put it into practice? Well, before we can actually go calculate a confidence interval, just like with proportions, we have to check our conditions. Okay? They're the same conditions. The only one that's an exception is this normal large counts condition changes slightly for means than it does for proportions. Our random sample still has to be collected randomly. And the purpose of a random sample, again, is still to reduce bias. This logic is still the same for means. The 10% condition is still the same 10% condition. My sample has to be less than 10% of my population. And the reason that we have to check the 10% condition is still to make sure that my data points are independent enough from one person to the next or from one measurement to the next. We have to make sure that my results are independent enough. And same thing, this is really only important when we're sampling without replacement. And that's really an AP thing only. JUCO's not really going to worry that much about this idea here with this independence idea. With replacement versus without replacement, but AP does, so beware of that. So the 10% condition still has to be satisfied. Now, my large counts condition, my normal large sample condition, this is where it changes. My goal is still to make sure that it is approximately normal. But we now have a hierarchy of conditions that we check here. Revert back to chapter 7. If you think back to chapter 7, the first thing we want to look at is if my population is normal, we automatically know that my sampling distribution is approximately normal. That's the easy one. If the population is normal, I know that when I take a sample out of that population, those sampling distributions are also going to be approximately normal. If the population is not normal, then that's where we use the central limit theorem that says as long as my sample is sufficiently large. And remember, for AP, we say that that's greater than or equal to 30. For JUCO, we say that is greater than or equal to 25. If my sample is sufficiently large, greater than 30, greater than 25, then the sampling distribution is approximately normal. And level 3 of that is if I have a small sample. It's not more than 30, not more than 25. If I have a small sample, we have to graph the sample data. And we're looking for no outliers and no strong skewness. And we will look at an example like this one in today's, you will look at an example like this on today's homework, where you're going to actually have to graph the sample data to see if there's any outliers or skewness and then be able to move on. So, same condition as we did in Chapter 7. There's a lot more to this, though, a lot more thinking. Oh man, I hate that dreaded 5-letter word where you actually have to think. There's a lot more thinking that goes on with means than there is with proportions. Now, even on the last test and even with this particular chapter, I still hear a lot of you trying to apply the central limit theorem to proportions. I'm going to pause it.
Pete Logan, would you call the office, please? Pete Logan.
Maybe I'm not.
Thank you.
Sorry, I couldn't find the pause button fast enough. So, Pete Logan needs to go to the office or call the office. But let's continue on. I want everybody to literally, I shouldn't say literally. I want you to think this out loud. Maybe not think it out loud. I don't know what I'm saying. We only use the central limit theorem on means. Say it out loud, think it, write it, whatever. We only use the central limit theorem on means. A lot of you keep trying to use the central limit theorem on proportions. There is a large gap here that you cannot cross. All the others are the same idea. The normal condition is not. Central limit theorem is only used on means. All right, I'll get off that soapbox. Let's move on. Standard deviation of the sampling distribution of sample means. By definition that we learned in the past, that was the standard deviation of the population over the square root of n. Once again, we don't know the population standard deviation, so we can't use this. We have to use the sample standard deviation. And so we have a new name for it when we use a sample standard deviation, because this number is not as accurate. There's more error in it. So because there is more error in it, we call it the standard error. And just as a reminder, this is also why we use T star rather than Z star. Because we don't know the population standard deviation, we use the sample standard deviation, so we have to use T star instead of Z star. Time for me to go home. Not really. Not yet. Let's finish this video up. So, in order to actually do the calculation, this is our formula if we're going to do it by hand. And just like on the homework for 8.2 with situation number 2, where you had to only work with just this part of it, you will be asked to break this apart and only work with certain parts of it at times. Now, if they ask you to do the entire process all together, yes, you can do it on your calculator using T interval. But if they ask you to break it apart, you're going to have to do some of it by hand. You'll have to break it apart and use the different components here. So, quickly remember, this right here is called my margin of error. This thing is called my point estimate. Or we also call it our sample mean. This part of it, just this S sub x over square root of n, this is called my standard error. And this T star thing, that's called my critical value. As you can see, and I've emphasized from day one in this class, and it's going to show up even more and more and more, there is a lot of vocabulary in this one formula. If you don't focus your mental energy on understanding the vocabulary and connecting it to an idea, you're going to struggle. You have to start working on connecting vocabulary to concepts, not just working on getting an answer. Now, last thing I'll say before we go to an example. When you go into t-interval, there are two options. I'm going to show this to you. On your calculator, when you go to stat, tests, and you go down there to t-interval, glare. Go down there to t-interval number 8. You'll notice right away there's two options. Data and stats. The number one question that I get kids asking me on the test is, which one do I use? And I'm going to say, I don't know. I hope you can read and understand the difference between data and statistics. What is the difference between data and statistics? Well, data is a collection of numbers. That's why it asks you which list your data is stored in. You should know that. What are statistics? If you go over here to statistics and hit enter, what are statistics? Statistics are things like the mean and the standard deviation and all those kinds of things. So if you go over and hit enter on statistics, you'll notice that what it asked you for changes. Now it's asking you for, oh look, the mean, the standard deviation, and the sample size. Okay? You need to know the difference between data and statistics. And you'll look at a couple of examples with that. So when you do t-interval, you've got to know, are we working with data or are we working with statistics? No, I will not answer that question for you on the test. All right, let's look at some examples. Turn to the very back page. All right, taking a look at this. Biologists are studying the healing of skin wounds measured at a rate called where new cells close the cut made in the skin of an anesthetized newt. I have no idea what a newt is, by the way, some sort of animal. So they gave these newts anesthesia, they cut them open, and then they measured how long it took them to heal. Here is the data from a random sample of 18 newts. Measured in micrometers per hour, calculate and interpret a 95% confidence interval for the mean healing rate in number of days. So we have a newt that took 29 days to heal, and we have another one that took 27 days to heal, and another one that took 34 days to heal, and so on and so forth. So how long does it take to heal on average? That's what we're looking for here. All right, so going through our 4-step process. Step 1, what is it we are actually trying to measure? Find your parameter, identify it, name it, know what you're working with. We're trying to find the true, whoops, I can't spell, mean healing time of newts. I don't know why it paused and froze there for a second, but on my screen at least it paused and froze, so I apologize. So that's what we're trying to find. Now step 2 is we need to check the conditions. So what we're going to be calculating is a t-interval for means. Our conditions: 1, we have to have a random sample. Does this data come from a random sample? Right up here in the problem it says, here are the data from a random sample. So we say this is from a random sample. Number 2, we have to make sure that the 10% condition is met. So, are those 18 newts less than 1/10 of all newts? I would say there's probably more than 180 newts in the world. I don't know what a newt is, but I would guess there's more than 180 of them. So we can say that these results are going to be independent enough. And then finally, we have to check the large counts or the normal condition. Are these data normal? Okay, well, this is where we have to go back, and this is this 3-step process we have to think through. Is the population distribution of healing time of newts normal? Is the population normal? Well, does it say here that population distribution is normal? We don't know anything about the population distribution of newts healing time, so we have to skip past number 1. We don't know anything about the population distribution. Number 2 says, is my sample size sufficiently large to be able to use the central limit theorem? Is it more than 30? Is it more than 25? Well, I only gave you 18 newts to work with because they're really expensive to buy. So we can't even use the central limit theorem. If this had been 30 or 50 or some number more than 30, we could have used the central limit theorem, but it's not. And I intentionally wanted to give you one in your notes where we had to go to that 3rd level. So, because we only had 18, we have to graph our sample data and make sure there's no outliers or no strong skewness. So how do we graph our sample data? Well, these data points up here, this is my sample data. It's the data that I collected. So how do I graph that data? Mr. McNeely, you're going to make us go back to chapter 1 and remember that stuff? Yes. Go to our calculator, and we're going to put that data into list 1. So going into list 1, we're going to type in our 18 data points. 29, 27, 34, I can just hear the grumbling now, and I'm not even at school. I'm at home, and I just heard a collective grumble at home. Yeah, it's the reality of working with data. You're going to have to type data in your calculator and work with it. Oh my goodness. All right, so we have our data put into list 1. How do we actually graph data now? Second stat plot is where we get into our graphs to graph data. We're going to plot data. We're going to go into number 1. What type of graph do we want to do? First thing we need to do is we need to make sure we turn it on. So make sure you press enter, and the on is highlighted now for this plot. What type of graph do we want to do? Remember, we have a histogram, we have a modified box plot, a regular box plot, and a step graph. Histogram is usually the best one to use, but you can also tell a distribution is normal or not with a modified box plot. In fact, I would recommend using the modified box plot when we're graphing this data. Why? Why do you think I would recommend using this modified box plot? Because it shows outliers. Remember, on that modified box plot, those dots over there are possible outliers. And so this modified box plot shows outliers, whereas a histogram won't. Okay, so I would highly recommend using the modified box plot. That means you're going to actually have to remember what a skewed box plot would look like versus a fairly normal box plot would look like. Make sure that over here your X list is your list 1, and your frequency, remember, is just 1. We don't want a frequency list, because if we put another list in here, that means that 29 occurs however many numbers there are in list 2. And 27 would occur however many numbers there were in list 2. So we don't want to, the frequency is how often do these data points occur. Well, these data points only occur one time up here. Okay, so we want to put a frequency of 1. Press enter on that, and then what do we zoom to be able to graph this histogram or box plot or whatever it is you choose to use? We press zoom, and we go down to number 9, zoom stat. So here's a graph of that particular data. Yes, I want you to sketch a rough sketch of that on your paper. Doesn't have to label it, just has to be a rough sketch of it so that I know you've graphed the right data. Now, what do you notice about this box plot of our sample data? First of all, there are no outliers. There was no outliers on that data. Second thing, is there any strong skewness? Well, what would skewness look like? You guys got to remember that back from chapter 1. Oh my goodness, I heard the grumble again. What does a skew distribution look like? This would be strongly skewed to the left. A long tail on the left. Remember, that would indicate the data would look like that. Okay, so a long tail on the left shows strong skewness to the left, and vice versa. Strong skewness to the right would look like this. This indicates a whole bunch of data on the right, and it's very spread out on the left. You like how I did that? I just flipped it over. Made it nice and easy to not redraw the box plot. But strong skewness is a long first quartile or fourth quartile. So first quartile, fourth quartile, if either one of those tails are really long, that indicates a really long tail on the distribution, so strong skewness. Does this graph have any really long tails? No, it does not, so there's no strong skewness. So because there's no outliers, no strong skewness, all of these things together, we can assume that it is approximately normal. Man, that's a lot. I know it is. So, we stated our parameter. We checked all the conditions. Now it's time to actually get to go do the calculation. We could do that calculation by hand. And I really don't want you to ever do it by hand if it doesn't tell you to. I would much rather you use t-interval on your calculator. Okay, much rather have you use t-interval. So, on my calculator, stat, tests, go down here to t-interval. And we're going to press enter on that t-interval. So once again, what type of information did I give you? Did I give you data or did I give you statistics? I wrote it right there to help remind you. I gave you sample data. So I'm not going to use the stats option in this t-interval. I'm going to use the data option in this interval. And again, it should be kind of logical, because where did we just put all this data? We just put all this data in list 1. So there should be some kind of logic involved in all this as well, that you can problem solve that a little bit. Okay, so my data is stored in list 1. My frequency is going to be 1. This particular problem asked me to do a 95% confidence interval. So I'm going to type in 0.95 and hit calculate. And it gives us our confidence interval, 21.527 to 29.806. It gives me my sample mean and my sample standard deviation. Those things might be beneficial for you as well. And then it also gives you your sample size. So for this problem, my confidence interval goes from 21.527 to 29.806. Now we've got to interpret it. we are 98% confident the interval from 21.527 days to 29.806 days will capture the true mean healing time of a newt. All right, so that kind of puts it all together. There's a lot going on there, a lot of little things, little nuances, but the process is pretty close to the same. There's just a little bit of weirdness that can happen because means create slightly different scenarios for us. So we got to be aware of that. All right, last little thing here, and I'm not going to do the examples for this. We will look at the examples and kind of talk through this a little bit more on Tuesday. But I do want to talk about this because this was on your 8.2 homework, and it's also going to be on your 8.3 homework. Choosing a sample size. We don't know what n is. It's the number one question in real, actual data collection, in the real world of statistics. The very first question you ask is, how many people do I need to go measure? How big of a sample size do I need to figure out in order to get a specific margin of error? For example, in election polls, we use that a lot. A lot of times election polls want a margin of error of less than 5%. So in order to get a margin of error of less than 5%, we've got to go ask a certain number of people in order to meet that. Same thing can happen with means. If we want a margin of error of less than 2 days, let's say we're talking about this previous problem up here with the newts. If we want a margin of error of less than 2 days, right now my margin of error is about 4 days. If we want a margin of error of less than 2 days, we're going to have to take a much bigger sample. So, how do we know how big of a sample we need? Well, it's this simple. It's this paragraph. We're going to plug our known values like Z star and T star and P hat and sample standard deviation or whatever it may be. We're going to plug our known values into the respective formula, whether it's means or proportions. So respective formula is talking about means or proportions. And then work backwards. So you're going to do some algebra work. We're going to solve for n, because that's what we don't know. So we're going to solve for n. Since we don't know the sample proportion before we're doing this, so we're trying to figure out how many people we have to ask. So we don't know what the proportion is because we haven't even asked anybody yet. Since we don't know the proportion before that, we use p hat equal to 0.5. For those of you that were working on the 8.2 homework, that is my conservative estimate. That's your conservative estimate for p hat. And the interesting thing is if you use 0.5, you're going to get the largest sample size. If you use anything smaller than p hat, your sample size goes down. It's a weird inverse relationship there that we can look at a little bit on Tuesday. But if we use 0.5 as our sample proportion, we're going to maximize our sample size. If we use a number less than 0.5, our sample size actually goes down, meaning we have to ask less people to be just as accurate. It's a weird kind of relationship, and we'll look at that a little bit more. But when we don't know p hat, we use 0.5 as our conservative estimate. Similarly, for means, since we don't know the population standard deviation, nor do we know the sample standard deviation, really we could probably just say it like this. Since we don't know either one of the standard deviation, actually, I said that wrong. I just now thought of the logic of this. It's not even standard deviations. Sorry for making you erase. I was thinking the wrong thing here. Since we don't know the sample size. Remember, in order to find T star, We have to know the degrees of freedom, which means we have to know the sample size. Well, we don't even know the sample size. We don't know the sample size. So we can't find T star. So since we don't know the sample size to find T star, we use Z star instead of T star. So when we're trying to find the sample size for means, we go back to a Z star distribution with a mean of 0 and a standard deviation of 1 to find that Z star critical value. And interestingly enough, what this will do is also give me the biggest possible sample size necessary. Because remember, when we go away from that Z distribution, the further away from we get it, the further away from the Z distribution we get, the smaller the sample gets. So a Z star distribution would be the largest possible sample size that we could possibly come up with. Again, we can talk more about that on Tuesday, but theoretically it makes sense to use Z star because it is the maximum sample size. Just like 0.5 will also give the maximum sample size. So those are our conservative numbers that we use when we're trying to find a sample size. All right, so for your homework, just kind of recapping this for your homework, the first thing you're going to be asked to do is to find the T star critical value using inverse T for 2 quick examples. Okay, inverse T, and remember to draw your curve with that so that you get your full credit. Then, for number 2, you're going to be asked to actually do the work like we were just talking about, where you have to find out how many students. You're going to have to work backwards with the standard error formula to get the value for N on number 2. And then number 3 down here is just a typical normal, do the whole process to find a confidence interval for the average weight of an Oreo and determine if it's convincing what they're lying or not, and so on and so forth. So, just like here now, notice what they give you here. They give you the standard deviation and a mean. They give you a mean of 11.3921 and a standard deviation of 0.0817. So when you get ready to do the T interval, on this one, we're going to be using statistics and not data. Because I did not give you the weights of all the Oreos. I gave you the end result, the mean weight of an Oreo, and the standard deviation of an Oreo. Okay, so on this example on the homework, you are going to be using T interval with statistics, not data. All right, we will look at this on Tuesday and review on Tuesday. Right now, your test is scheduled for Thursday next week, so be ready for that. Tuesday will be kind of a day of catch-up. I've got a little bit of practice for you to do, but then we will test on Thursday next week. If you get stuck or anything like that, feel free to email me. Otherwise, we will see you on Tuesday. Have a good night.